Okay, kids, this really is the last topic of the year. Still in polar curves, still doing calculus with polar curves. We've done slope, right? We've taken care of slope. We've written the equation of a tangent line, dy dx, found the expression dy dx, plugged in a value to find the derivative at a point, and again, written the equation of a tangent line. Also talked about the rate of change of r with respect to theta and what that means for movement around the polar curve. Then we found the length of a polar curve. It still was the integral of Pythagoras, but it was r squared plus dr d theta squared under that radius. Now we're going to do area. So here is a polar curve. Again, it is, you do not need to know what it is called. It's a cardioid. You don't need to know that. You don't need to graph it. You need to be able to recognize it here that it travels, the period of cosine is 0 to 2 pi. So, right, when I start, right, however I travel it is going to take me 0 to 2 pi. It is a polar curve r in terms of theta, right? R in terms of theta. And if I want to find the area inside there, it is pretty intuitive, this part, right? I want the whole thing. So area is going to be integrating. Now, I'm just going to give you the formula, but again, if you realize and remember, when I'm graphing, right, I go out a certain radius and then rotate, right? So these are like sectors of the, if I take really, really small slices of all these polar curves, kind of approximate the area of a triangle. I want you to think the area of a triangle has a half with it, right? And I'm going to sum all these up. There's my formula for the area inside a polar curve. You are dealing with thetas, and you're integrating with respect to theta. You are going to put r in here, your expression for r in terms of theta, and you're going to square it. And you are going to multiply it times a half. So of course you can osmosis the half out here. The half does come from the formula for the area of a triangle. The r radius getting squared has to do with, again, developing through the formula when you're writing your base in terms of r, all this kind of stuff. You just need to memorize that formula. A half, and then it's r squared. That's it. Okay, so bam. I take r, put it in my formula. Notice since I want the area inside the whole thing, I'm going from 0 to 2 pi. I have my 1/2 that I can keep inside or osmosis outside. I'm going to put that that r inside there, and I'm going to square it. I have my calculator. Now, I showed you a screen. If you're in polar mode, this is how things are. Like, suppose I was graphing this in polar mode, so I already had it in R1. Right, you know how you did second, right? Second vars and arrowed over to y vars, and then you just chose function. Well, if you arrow down one of your things, you have polar, and so you can pull up R1 and square it, and you can do all of this in your home screen in polar mode, or you can go back to regular rectangular mode, and you can hit 1/2, 0 to 2 pi. Put this equation in y1, call up y1, square it, dx, and you will get the same thing. When you use your calculator, you will not get 6 pi, but you will get 18 point blah, 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 and it is 6 pi. Okay? That seems pretty easy. Well, it is with fairly simple curves. Now, if I only wanted a piece of this, I could say, oh, I only want going from 0 to pi, right? I could just chop this right here and go from 0 to pi, right? But what if I want to do the intersection of two? So to find the area between, I shouldn't even really use the word between. I should use the word area included between. I don't know. You'll see. Sometimes it's not so bad. It is just like finding the area between Cartesian curves. So do you remember that? What did we do when we were doing, right, trying to integrate, right, like when we were doing top minus bottom kind of thing, right, between two curves. We would need to find the intersection points to put here. So between, sometimes it is just a matter of finding who is your larger pole, which of your polar curves has the larger area, squaring it, and subtracting off who has the smaller area, squaring it. It is not the same as capital R minus little r squared, right? And these are your thetas of intersection. Sometimes it's as simple as that. So here's a problem from your book, number 55. Find the area that lies inside the circle with a radius of 2, so your center is going to be at the origin, and outside this cardioid. Again, you would either have a calculator or we will give you this graph, either one. So let's see if we can figure out, let's see if we can picture where this is, right? The circle of radius 2 is here, right, with the center of the origin. So I want to be inside this circle, but outside the cardioid. So inside the circle, but outside the cardioid. That's all of that right there. Do you see that? So I need to find those points of intersection. How do you find the points of intersection? No matter where you are, anytime, any place, anywhere. You set the equations equal to each other, right? Circle of radius 2, where are you equal to the cardioid? 2 equals 2 times 1 minus sine theta. Divide both sides by 2. Negative sine theta. Subtract 0. So where is, subtract 1 from both sides to get 0. Multiply if you really want. Where is sine of theta equal to 0? Well, hello. Theta equals 0 and theta equals pi. That is not too surprising, right? So here I go. There's my 1/2. Again, you can osmosis the path 1/2 out here. Here is the points of intersection. Theta equals 0, theta equals pi. Who had the larger, or who was, right? Where did the most of it come from? Was the circle, right? Can you tell that most of the area is from the circle? So that's why this is capital R 2 squared minus the smaller area that I'm taking out, right? Because I'm just taking out these two little bumpy things. D theta, plopping that in my calculator. And again, you don't have to be in polar mode to do it. But if I was graphing this in polar mode, the equations are already in R1 and R2. So again, on your calculator, if you hit vars, arrow over to y vars, and choice 3 is polar, then you can pull up on your home screen R1 and R2. And I get some number for this. If your calculator is taken away from you, oftentimes they'll ask you to set up but don't evaluate, something like this. So that one's not too bad. Not too bad. Now, some of the things, before I go to the next problem, and you're going to need this thinking, I want to try to, again, remind you of graphing in polars. What's happening is that you are going from the pole, right? And if I am going along this cardioid, right, to do the cardioid, I am going out a radius and then sweeping, my theta is sweeping me here, and then sweeping me right to pi, right? Radiate out, going 0 degrees. Radiate out, going a little bit of radians. Radiating out, right? And that's why the cardioid I subtracted off. Whereas for the circle, you're going out this radius here and then traveling all the way to pi. Now also notice that because of the beautiful symmetry of many of these polar graphs, I could have just gone to pi over 2 here and then multiplied my final answer by 2. Couldn't I have? Couldn't I have just found this piece here, gone from 0 to pi over 2, and then multiplied that area, my answer, by 2, right? Use symmetry when you can. All right, let's look at this one. This one's not as nice, right? So sometimes dagger. And it's often not obvious when it's a dagger. You got to draw it. And you don't have to draw the shapes yourself. You have to either use your calculator or the graph will be given to you. So look at this one. Find the area shared by, this looks pretty nice. 2 circles. There you are. Can you tell which circle is which? A circle with a radius of 1 has the origin at the circle, at the center. So I want to find the area shared by the circles. Can you see that area? Can you visualize it? It's right here, right? But look at the problem. Do you see the problem? Do you see why this is going to be a dagger? The bottom here of the area that I want is defined by 2 sine theta. And the top of the piece I want why won't it change colors for me? Change to red, please. Red is on that circle. I think I am going to use symmetry here. I think I am just going to go after this and multiply my final answer by 2. Now, the problem is, how do I graph that? It's not just top minus bottom in polars here, right? Because I need to figure out of this red circle, right? Of the red circle, I need to only go from this point of intersection to here. But from the blue circle, I need to go from, right, the blue circle, I need to take off piece. What is going on? All right, hold on. Oh, my dog is out here. He's going to start barking. All right, hold on. Let me take some of this stuff off. Let me just back up. Firstly, let's look at let's look at that place of intersection. Now, I know there's another point over here, but remember, I'm going to end up with using symmetry and multiplying by 2. So where's my point of intersection? Where is sine equal to 1/2 in the first quadrant? Right? That's pi over 6, right? So I'm going to draw a radius out through pi over 6. Now, look at the blue circle. Blue. There's my blue circle. So I'm going to be starting at 0. My first radius is 0, 0. And then I'm going to go out here, out here, out here, and out here. That's how I'm going to get that piece. Then I need to, oh, stop it. Then on the other side of that radius, I need to radiate out to which circle? I need to radiate out to the red one, right? and stop where? Duke, stop. Come on, you're going to have to go in. Hold on. Sorry, kids. Come here. Come here, puppy. Come here. You can't behave yourself. Come on. Yeah, I know. Come on. I know you don't want to come. Come on. Somebody's waiting for you. Come on. Duke. Come on. Oh, do you see her? She just does not listen to me. Come on, puppy. Come on. Come on. Come here. Good boy. Come here. Come here. Good boy. Come here. Duke. Ah, not good boy. Come here. Come here. Oh. You are showing all my students what a bad boy you are, that you will not listen. Here, you know what? Let's go outside and bark your head off out here. They can still hear you, but not as loud. Bye. Oh, he's not the brightest, the poor thing. He's really pretty, but he's not very bright. So he's going to bark his head off at the trees blowing out there. Okay, sorry. Sorry for the distraction. Okay, here we go. So, do you see what I've written so far? What have I done? I've done blue. Right? Here, going from 0, theta equals 0, to theta equals pi over 6. On the blue one. That gets me this little sliver right here. What do I have to do? Do I need to add or subtract from that area to get the area that I want? I am going to multiply times everybody times 2, right? But what do I need to do? I'm going to stop now. I'm changing boundaries. This is just like we did in rectangular, right? I am jumping from my blue circle to my red one, right? I'm changing to the red one. So I need to, and this time I'm not subtracting. What are you doing? Adding. Notice where I started. I started at the red radius here, which was at pi over 6, and I'm going on the red circle from pi over 6 to pi over 2 and using the same formula. There's my 1/2. There's my r squared d theta, right? I put these squares, try to write, don't forget those squares. And then, of course, obviously, right, this 2 is just going to wipe those guys out. And I'm just plopping everything in my calculator, and I got 1.228. All right, so that took me some time. That took me some time to very carefully figure out what did I have to do. So think about the first example. There really wasn't too much thinking. The whole piece, right? I had one curve, and it was going from 0 to 2 pi. I wanted the area of the whole thing. Went from 0 to 2 pi. Bam. The second example, I had 2 curves, but I had overlapping pieces where I needed an area and I had to subtract. I had a bigger area and I had to subtract off a smaller one. But I could keep the same integral, right? Because I didn't change boundaries. Here, though, I changed how I had to, right? And when my 2 separate pieces I needed to add together. Right? So yes, this is a little bit challenging. We will do another example when we're in our live session. And of course, you have some homework to practice. And then we will practice this some more before we have to worry about our test. Okay? All right. Excuse me again for my dog barking his head off. And I will see you in our live session.